Hi everyone and welcome back to Line. Today we are going to perform a binary classification on 3D point cloud. So we have currently a dataset of several 3D point cloud, for example chairs, eagles and other objects. The goal is to be able to say, given 3D point cloud, to say if it's a chair or not, yes or not. The first thing we need to do is to do a feature extraction. The question is how to perform a feature extraction and which kind of feature we can extract from that. Then also which kind of machine learning model we can use after extracting the features and build a dataset, which kind of model will be adapted to that. To answer these questions, let's go ahead with the presentation. So the first thing is the feature extraction, and I called here entropy function. We are going to see that exactly in a few. So the feature extraction, the fact that we have our dataset and we need to extract the feature. So it can be the shape, it can be the number of points, it can be the width, the length. We can also perform principal component analysis and extract other features. Also in Open3D, as you can see here, we have functions that provide currently a 33-dimensional vector that describes the local geometric property of a point. I think this is a great feature extraction we can perform in order to get like a great description in a single vector of only 33 dimensions of a current 3D point cloud. These features are also used for the RANSAC and the ICP iterative closest point registration between point cloud. But we can also think on other features and then to build a dataset with them. Now the question is, after I get my features, how I can measure the relevance of each feature? If I need to choose the most relevant one, which measure will provide this information? So this is the concept of entropy. Entropy is a fundamental concept in thermodynamics, theory of information, and statistical mechanics. It represents the measure of disorder of or uncertainty in a system. For example, in thermodynamics, it represents the current change of entropy, represents the change of heat exchange by the temperature. In statistical mechanics, for example, is the number of microscopic configuration. Now, in our system, in machine learning, the entropy of a dataset is calculated using this formula, minus the sum of the probability of an event times the logarithm of the probability of this event. If we have in the binary classification, we have yes or no, so we will have minus probability of plus logarithm of probability of plus minus probability of no logarithm the probability of no. Now in this image we can see two images. So in the left one we can see only lions, and in the right one we can see several animals, okay, giraffes, elephants, also dogs and cats and so on. So the question is, which of these both images has the higher entropy? If I said the entropy is a measure of the disorder of a system and the measure of unpredictability of a system, so I can ensure that the highest entropy is in fact in the right image. Why? Because in the right image I cannot predict very easily what will be a next object, a next animal in this image. So let's take an example. If I say I have a new animal and I want you to be able to predict which animal it will be in the left image or in the right image, it will be easier to predict that in the left image because we have only lions. So the probability to get a next lion is very high. But in the right image, the probability of getting an animal, a lion for giraffe, is very depends of the number of giraffes and the number of elephants in that. And because the disorder is high, so the entropy is high. So now, if I want to select the most relevant feature, we understand that it completely depends on the entropy. The information gain is currently computing the using this formula, and we can see that it's based on the entropy. But the most important thing regarding the information gain is that the information gain provides the reduction in entropy. is a measure of the reduction of the entropy achieved by partitioning a dataset based on a particular feature. It's used to select the best feature for splitting in decision tree algorithms. So the decision tree process is like that. The first thing we need to do is to compute the information gain for each feature, then to select the feature with the highest information gain, which is again measure the reduction of the entropy, which is a disorder. So we want the less disorder as possible. We want something very ordered in order to predict something like that with it. So we need to reduce the entropy, and so this is the highest information gain as a root node, and recursively apply the algorithm to partition the dataset further. So now we want, in this project, we want to build, first thing we want to do is to build this table. This table, as you can see, we have the name of the object, we have several objects, we have the number of points, we have the length, the width, and the height. This is already suppose that we performed a principal component analysis in order to get the orientation of the object, and then to get the length, the width, and the height. Then the density, the ground distance to the z, because, for example, if I want to define if it's a chair or not, so the ground distance needs to be low. It's not like a giraffe, which is the ground distance will be high to the z-axis, and the aspect ratio of the length by width and the aspect ratio of the width by height can be also important. So let's go ahead with the code and how to in fact perform this thing. So just a brief review of the code, and then I'm going to execute that, even not in debug because it's a simple code. So we have several functions: download file, we have also load point files, NumPy to point cloud, several functions, load Open3D samples, generate object variant, compute OBB dimensions, so for the bounding box, extract features. So this is important. In extract features, you can see we have the number of points, for example, we have the length, width, and height by using this function. You can see further, we have the volume, when the density is in fact the number of points divided by the volume. We can see also the points to compute the ground distance. This is the mean of the point in the z-axis, okay? We have the aspect length by width and the aspect width by length, and then we can build the table with these things. So the idea is currently to generate a data set of several point cloud, also of several 3D objects, and then to build these tables. So let's go ahead with that. So we have now this one. Let's continue. Okay, great. We have now another object. So this is an eagle. Okay, you can see here's the bounding box computing using PCA of Open3D, and then we extract the features as well. Another object which is bunny, and again the goal is to define if this object is a chair, yes or not. And this is important to precise that we are not going to provide the full object to the decision tree. We are going to provide only a part of information from this object given by the feature extracted from this object. So this is again a chair without a color. Eagle. Okay, so several objects. Now what can be interesting is to see the table. So we have here, let's show that, we have here the table with the numbers, and we can see that I get the number of points. So for the eagle, I have more points. We can see that it's a sampling in difference. We have the length, the width, the height, the density, and so on. The question is also, what do you think about that? Do you think this will be enough to define if it's a chair or not? This feature extraction can be enough, yes or not? I don't know. At this stage, I would say it can be interesting to try it and to compute with the decision tree this binary classification, but we need to be aware that in general, in 3D point cloud, in images, and in gross data like that, we used deep learning. Why we use deep learning? Because again, the main difference between machine learning and deep learning is that deep learning extracts the features by itself. So it doesn't need us to extract manually the features like we do, but it's more expensive. It's a lot of training time. It's require GPU and some also other stuffs. But in machine learning, if we have a system and we can extract relevant features, so we can use that. So now we need to determine if to make sure that the features we extracted are relevant features. So now I also choose to partitionate the numbers into low, high, or medium. And the goal of the next video next week will be to take this table and to try manually to compute the entropy, the information gain, to define which of these features is in fact the most important one. And then when we have the most important one, we can take this feature and put in the root of the main node of the decision tree. And then we can do the same thing for other features and build our decision tree. The last thing I want you to know is that decision tree is a key algorithm in machine learning. It's not always used as is, but it's used, for example, part of other algorithms. We have also random forest. We have also several other algorithms. Let's say random forest, you know it. Okay, sorry. Forest algorithm. Yeah, we can see here. We have also XGBoost, which is gradient boosting. We have several system of gradient boosting. It's currently training on the error and several ones. So that's it for this video. Thank you for listening to me. Share this video, share on LinkedIn, on YouTube, and continue to subscribe to the channel and like and leave your comment if you want me to share a video on a specific topic. Thank you and see you soon.